our section. Let's start our section now. Tharnier Puel will talk about Magnon-enhanced spin-based transduction for coherent microwave-to-optical conversion. Okay, so.
Thanks for introduction. Especially thanks for the organizers and those who were more deeply involved to my invite here. Thank you, Eggs. Thank you, Michael. Although I've been here many times, it's my first time actually giving a full talk. So I'm especially happy to be here today. And what I want to discuss and tell a story this morning is about quantum transduction. But I'll find my way to introduce you to some other things that we've been doing in the group along the way. So I'll start with a nice introduction that would take some time from my talk, because I want to touch several different things. I was very happy to see that Bill before me gave a nice introduction on cavity systems and the couplings, because that would be very helpful, and you save my some of my time and trouble, because I saw if you go into fundamental physics, how much trouble you can get into. And then I found my way to discuss how Magnon can help on quantum transduction. I'm also happy from working with Michael because he put me in collaboration with so many nice people, very smart, that helped me in everything that we'll present today. I'll mention some of them will be here next week, so I'll point to this. And before anything, I should at least define what do I mean by quantum transduction. So by quantum, I mean you're converting, by transduction, you are converting a quantum information between two frequencies. In this case, it will be microwave frequency, which is about 10 gigahertz, to optical frequency, which is about 200 terahertz. So there is a huge energy difference here that needs to be compensated somehow. Why should I be concerned about this transduction or this conversion? Is because microwave is good for a few things, optical are good for other things. So microwave is like a spin qubit compatible. Experimentalists may say that and help to explain why the phase and amplitude are much more stable and coherent than optical. I think it has to do simply with the wavelength that's so large. However, it's not good for everything. There is this thermal occupation. If you work at room temperature, you occupy those states quite a lot. So it's hard to do anything, any quantum in this regime. But if you insist on working with it at low temperature, it also has a transmission problem, because it attenuates very quickly. So after a kilometer, you basically lost your signal. And then what we do is we try to convert this information into an optical, which has a high bandwidth, lambda is small. It has a very low attenuation, so after a kilometer, you still retain 95% of its signal. The thermal occupation now is basically zero, because the energy difference is so high, so much larger than the thermal. But it also comes with its own problem, which is the cryostat. The cryostat, it works at very low temperature. It's hard to keep it cool. And then if you come with a laser, it causes heating. So this is one of the big issues in the quantum transducers that we have nowadays. But if you're really persistent and you want to work on the microwave only, you don't care about quantum transduction, you can. People have done it in Zurich, this Andreas Wolfer group. They took two cryostats, so this is one cryostat, this is another cryostat, and they tried to couple with a microwave waveguide. So you can do this kind of coupling if you're super persistent, but you see how much trouble it raises. So it's short distances, it's inside the lab, it raises a lot of costs, right? So it's especially useful if you can convert, because then you just use optical fibers and you transmit your signal. And yeah, I was told that I look like this person, but that's not me, unfortunately. It would be nice to be involved. It would be nice to be involved in this project. It seems fun. So what is the type of systems that actually do transduction nowadays. So there are different physical mechanisms used to do the transduction. You need to couple somehow a microwave with an optical. So it's not an easy task. So one of the most, I think, successful implementation is this optical mechanical, where they have this thin membrane that vibrates, and you shine light into it, so it transfers momentum, and then vibration is microwave, the light is optical, and then you couple the two. Yes, it is efficient, and yes, it's easy to integrate in a circuit, because people have done it, have demonstrated many times. But it has a very narrow bandwidth, and the coupling is especially weak between the light and this membrane. This is a few references, but I'm sure that the literature is quite extent, right? I'm not trying here to show any special. I think this is among the first. I don't even know if this is the first. So it might be outdated, the references here. So I excuse for that. But then there are more mechanisms. You can use piezoelectric effect. You can use Pocket's effect. There's a straight coupling between optical and microwave. And they all have their pros and cons. There is this Rydberg states, which are actually quite efficient. It can be more efficient than the 50% required for any quantum information processing that people discuss. But it's very hard to integrate those lasers into a circuit, right? So this raises issues. But there are more. There is Faraday effect that was discussed here this other day. There is optomagnonic with the whispering gallery modes, and actually I was very happy to learn yesterday what is the actual mechanism that couples the magnet with the light here in this case. It's some tensor that was introduced yesterday. I forgot the name exactly. But it's something that I had questioned myself. And because this is actually a focused conference, I have hopes that I learn a lot from here. Right? I don't know everything. And I actually am learning. And finally, let me introduce you the atom-assisted transduction. This is where my work goes in. Right? So we'll try to improve this implementation. So I go into some details, explain what the atom-assisted quantum transduction is. I will not go in details in the other ones. So here is a basic, I don't like the word basic, but this is a picture of how I think in the beginning. We will improve that thinking later on. But imagine you have a microwave at 10 gigahertz that you want to couple to some energy levels coming from an atom defect, for example. This is what I'd be thinking. It's some defect in a host material, and this defect has energy levels quantized inside the gap of this insulating material. And we access those levels. And the requirement for this atomic structure should be, one, it should have an optical transition. So the optical is from some ground state splitting to an excited state splitting. This is the optical transition. And it also requires to have some splitting in the ground state itself. This is the microwave splitting. It can be due to the Zeeman term, an applied magnetic field, or some natural splitting. So of course, I think most of you are thinking on the NV center, but this model is simpler than the NV center. NV center has a ground state that's spin 1. And then here I'm thinking on a spin half. So I only have a Kramers doublet, right, spin. And I'm splitting them by the Zeeman term. But if everything works out, you can couple this transition, spin flip, to the microwave cavity with some coupling GB. You can couple the optical transition to the optical cavity with some coupling GA. But you need to compensate with the energy difference if you want to connect the two. That's where an external pump comes in. So you have a laser that will tune excitations from this level to the excited level to compensate to the energy difference. So you are adding energy to your system. And, well, this is some area that I'm not expert, so I just raise some ideas. You can buy it or not. But why would that be particularly useful on the quantum is, well, imagine you have a cavity with some qubit encoded in it, believe me, you can encode a qubit state inside the cavity population. So you have a superposition between n plus 1 number of photons in the cavity, and then you can encode a qubit there. And if everything works out as I plan, and as I'll discuss here, you can strongly couple effectively this cavity with that cavity. So that means if you're working in the strong coupling regime, that means everything that's coupled in your system is much stronger than any decay rate. And in that regime, you cannot distinguish internal components of your system. If you can distinguish them, effectively all you have is a cavity coupled or connected, this one and this one, you can transfer state between the two cavities. Another possibility would be a flying qubit. So flying qubit is a qubit encoded in time. So you have the earlier flying photon, a later flying photon, and they are entangled. And then imagine that you can quickly convert the frequency of one into optical, and then there is a later one and convert to optical. So this is two different implementations that I don't have much details on the calculations, but some ideas that's out there, how you can use this transducer. I know I'm raising here more questions than answers, but I hope it works. So the idea of the atom is you take a photon from this cavity, you excite here, and then with the pump you excite there, and you wait for it to decay. When it decays, it radiates a photon that populates that cavity. That's your conversion. Or you can do the other way. It's both directions. You have a photon in this cavity, it's absorbed, you pump it down, you bring it down, you populate it here. If you wait it to decay, it takes a lot more time. But if you wait it to decay, it populates this cavity, so you transferred information from the two cavities. So that's a basic picture, more naive, but that's the basic picture of the quantum transducer. Well, and then you might be thinking, okay, you have an atomic level. What system should I use for this discrete energy levels? And the system I want to work with is lanthanide for the reasons I will explain next. So why lanthanide in this case is useful? Well, if you go to the free ion of a lanthanide, you see that it has atomic level occupations, and what you'll notice is if you look at the density of states, how they populate those, you see that near the Fermi level you have the 4F occupied. You also have D, but this D I will avoid by saying that I'll work with trivalent lanthanides from now on. Trivalent lanthanide means they lost 3 electrons, and that's a very stable configuration. So many people work, that's not theoretical, so the trivalent lanthanides are actually the most stable configuration in most of the setups. And then the 4F is actually near the valence, and the 5p and 5s shell, they are deeper in energy. But at the same time, it's counterintuitive because they are deeper in energy, but if you look at the extension of probability of occupation of those shells, you see that the 5s and 5p, they are further away from the nucleus than the 4f, which means the 4f is shielded by these complete shells, 5s and 5p. And this shielding is actually what is important for us, because this shielding leads to a variety of things. It leads to an isolated 4f. It means that anything that survives for a long time because the environment doesn't have access to it. It leads to narrow line width, especially in homogeneous, because this coupling to the environment is so weak. Well, it also has, right, two sides of a coin, which is it has a slow photon emission. It survives for a long time, but the decay rate is very slow. So if you want to read out anything that's coming from that state, it's going to take a long time. And especially what I would contribute to is this weak coupling to the microwave. And the weak coupling, I also don't have a very deep knowledge on why the coupling is especially weak, but I can understand by the compatibility between the wavelength. So the wavelength of microwave is so extended and the atom is so localized, it's hard for them to exchange. So there is a weak coupling in this microwave frequency. And the coupling is special because this microwave coupling is due to the magnetic component of a photon, not the electric. The electric will couple to this atom via an optical excitation. Okay, among the lanthanides, there are many, there are several, so I should pick one if I want to work with. And by looking at the transitions of each ion, not me, but we can notice that erbium is the only one that has a transition right at the bottom of the attenuation of a signal going through an optical fiber. And this minimum here is right at where the erbium has a transition. Some others have nearby transitions as well, but erbium is the only one that has a transition with no states in between, which means you don't have any other channels for decay. So, I mean, not from the erbium itself. So, erbium is a very special case in this regard, because it sits right there where it should be. But of course, God gives you to one hand and takes from the other. So, when you go to a host, and you sit the erbium there for substitution. So you have a host, and you want to replace one atom from a crystal and put erbium instead. So there are many hosts, and each one is good for one thing and worse in others. So there are many hosts that has been used. And what is special is that this yttrium, in most of the case, or zinc or titanium, they are very good substitution for erbium. So erbium sits in there without distorting too much the lattice itself. But it comes with a cause, which is you split those degeneracies. That degeneracy that exists in the ground state of erbium, now it's splitted. So each level that I will call multiplet will be splitted. And why am I going into details about it is because describing that split is, you can effectively describe, but you don't have any confidence on the wave function that you produced. You can feed the energy levels, that's fine, but the wave functions are not especially accurate. But we, together with this group, Rashid Zia and Juan David especially, from Brown University, we worked very deeply to understand this semi-empirical description of what happens to the electrons in the 4F shell. So the electrons in the 4F shell, they are suited for environment that's good for me, but at the same time they have a strong correlation between electrons. So you come with a Hamiltonian to describe this, doing the minimum approximations that you can. And some people ask me whether this Hamiltonian is strong correlated. It is. But everything that I cannot calculate, that I don't know, and that I don't understand, I will hide inside the parameter. So in this Hamiltonian, there are the small letters in front. They are coefficients that carry all the strong correlation in Coulomb repulsion between electrons that I don't know how to solve. So what can I solve? I can solve the angle dependence of those terms. So the angle dependence comes with some operators, and everything is encoded in this Hamiltonian. Well, why is that particularly useful? That's particularly useful because now I can describe the energy levels in not so much effective way. I can describe all the spectrum of the 4F electrons in a crystal, in a host. And this calculation is rather intricate. So we worked together with this group to offer you a code that has easy use, very user-friendly, and you can use this code. It's free. You can just download and then generate your energy spectrum. You have parameters. You do your own fit. So we want to encourage people to use that and explore more data, because we are very few in data with this much of energy spectrum. Many people nowadays, because of quantum, they only work in these two levels, so the ground state and the excited state. But very few have been looking for all the spectrum. And the spectrum is required for us because we have so many coefficients. We need many energies to have a good fit. So once you have developed this, and
I have a question. Excuse
yes.
me. Sorry.
So how do you come up with this model? I mean, what do you take into account to derive the model?
It's an excellent question.
Okay.
I did not come up with the model myself, but the model carries, there is a mapping to this Hamiltonian that you see, and the mapping is well described in this reference, but it carries first, there is the basic shell description, and then you have some, relativistic effects that has to do with the spin-orbit coupling, spin coupling of different ions, orbit coupling of different electrons. So we go 2 or 3 more non-usual terms on this relativistic approach. But the most difficult part actually comes with the fact that we take into account some population of D levels and return to dF. That causes some effect, some perturbation on the F electrons occupation themselves. So there is some perturbation theory used behind, and it actually affects all the parameters. And this perturbation comes with the fact that you populate the D, come back to the F. The Hilbert space here is solely the F electrons.
But do you use tight binding? Or what do you use to derive the model?
I don't know. We use this Raka algebra. We use this Raka algebra to describe the mapping between the symmetry of the crystal.
Oh, so
that
you
affect
use the symmetry of the crystal to
Yes.
derive the Hamiltonian. Yeah, that was
Yes.
where I was going to.
Right,
Okay.
right. But the reason I say I don't know is because the Raka algebra is not something that I followed through all the way. So I rather understand how the things are connected, and I use this Hamiltonian. But it comes a long way. It's not recent. So it's being tested by many smart people, smarter than me. I believe them, and that's correct. All right? So I was saying that this approach is particularly useful against the effective model that only goes to the ground and excited state, because we are on the Hilbert space of 4F occupation, where we have the description of the angular momentum and the spin separately, not only some effective total angular momentum J. So that tells me that the ground state is not only 15.5, as the effective model tells, but it's a superposition of different states of 15.5. So this is the term symbols that says that the spin can vary, the angular momentum can vary, but you have the same 15.5. That gives us confidence to calculate something else from the wave functions. So from the wave functions, we can calculate magnetic dipole transitions. We can calculate electric dipole transitions that in this case happen to be forbidden because we are transitioning 4F to 4F. We conserve the angular momentum you cannot have. But because of those distortions on the lattice, you allow some weak coupling via electric field between 4F, 4F. This is called forced electric dipole transition. But nonetheless, we have the G-tensor calculation that we also trust because we have some confidence on the L and S. The G-tensor itself is L plus GS. So we know how to operate in each of these states. So we can more accurately describe the G-tensor and all those. Yes, I know the G-tensor caused questions.
So you explained that you use symmetries to derive the Hamiltonian, but then you have very specific numbers in front of those kets. So how did you get those specific numbers?
Right. So those specific numbers are for erbium in lanthanum fluoride. Lanthanum fluoride has its own symmetry, I forgot, monoclinic, I forgot. And then I diagonalized the Hamiltonian and got the energy spectrum, look at the wave functions, and the wave function look like this.
Yeah, symmetries just give you the form of the Hamiltonian. They don't give you the parameters. So do you have some empirically determined parameters that you used for this?
Fitting. So we fit. You see this experimental. So we have here about 100 levels.
Spectrum. Okay, now I understand. Thank you.
You understand?
Yeah,
Okay.
Thank you.
This is a simple fitting. including those parameters that you might be thinking called BKQ, which is the Stevens operators.
More questions? No.
Right.
It seems that the ground state is not normalized. Or
It is. It is. It's just because
you have more.
I might be plotted here the coefficient and other coefficients squared, but it is normalized for sure. It's
Yeah. Okay.
it's just misattention from my side.
Yeah, I think it's missing. Yeah, probably.
Yeah. Probably, but believe me, it's certainly normalized. Yeah.
Okay.
What was I saying? Oh, I wanted to mention that the Stevens operator coefficient regarding to the symmetry, some of them are non-existing, so you should take that into account in your Hamiltonian when you do the fitting. So having said that, we investigated further a few things like keeping the free ion, what we call free ion parameters intact, and then you try to fit the crystal field coefficients to other type of hosts, and that's what we have here in this tube. So it's been fun. So I know that I need to come back to quantum transducer at some point. So here we are. So this is the Hamiltonian that we can come up with the simple energy level system. So you have an optical coupling here. This will be this E times the dipole, and then we have the microwave coupling. This is the E times the microwave. This is the B times the spin, which is a spin flip. Then we have the pump. This is the pump. And then we have the other terms like the Zeeman and the atom energy levels itself. So all that I described for the erbium before, it fits very well for this part of the Hamiltonian. And then you come with the cavity, as I said, you have the coupling. But in the regime that we want to work in is we want to generate a very strong coupling. We need this impedance matching. And then what we need to do is to match the frequencies. So the frequency of the excitation, the optical, should match the frequency of the pump and the microwave, like you see in this diagram. But not only, you need to be slightly detuned because you want to work in this adiabatic limit, but you don't want to populate those too much. You want to work in this virtual excitation. And then you basically ended up with a effective model that has the population of one cavity and the population of the other cavity. And just in terms of to be more solid, this seems very nice. It seems to work. It's a very nice idea. But is it actually someone have tried to do it? And you are very lucky because yes, people have tried to do it. And especially this earlier work of Longdale. And Longdale, for those who will be lucky enough to be here next week, he'll give a talk, I think on Tuesday. Let me see if I have it here. No, Monday. So Monday at 4 p.m., Longdale will give a talk here. I won't be, I'm sorry for that. But he basically put together a microwave cavity. This is this large chamber that you see here. And then he threw a laser. The laser reflects on this side, reflect on the mirror on that side. This is the optical cavity. And inside here, there is this yttrium silicate with erbium in it. And then he actually measured this transduction through the mathematical approach that I just described. And he could see that by tuning the frequency of the two cavities, you can get a very high 10 to the minus 5 efficiency. And the question is, how can we improve this efficiency? That's 10 to the minus 5, a lot of orders of magnitude to be improved, and people have improved that. I'll show in the next slide. But what I notice here is how narrow is the region you can work with. So the bandwidth is very narrow. You can see that the optical coupling is about 2 gigahertz, but the microwave is 40 megahertz. So the microwave coupling is weak. So what they did to improve the microwave coupling is now you take a smaller cavity. When you take a smaller cavity, you confine the photon, and then the coupling string is larger. And they put this on chip, they're smart, this is Andreas group, and they could improve a lot from 2 to 10 gigahertz the optical coupling, and they could improve from 40 to 100 megahertz the microwave coupling. Well, there are some problems that came with it, which is the optical loss in this type of coupling, it's large, but the optical loss is also large, causing heating. And the bandwidth is even narrower, it's like 500 kilohertz. And this is where our idea comes in, is where the Magnon comes, is imagine that we can improve this by a lot. Instead of fighting for a factor of 2 or 3, imagine that we can have a coupling of 2000 megahertz, which is 2 gigahertz. And that's possible, has been demonstrated in this work, where they couple, I think this is already published, I'm sorry, I apologize, I forgot that. But they have this they have this, what is that? Well, there is a microwave cavity in this long thing here, and then there is a magnet, which is this ink film, and they measure the coupling is very strong. So imagine that instead of coupling the microwave cavity to the spins, we couple the microwave cavity to the magnet. And the magnet will be coupled to the spins. So we have this other path. So just to be sure, we have until 11.
11:40.
Oh, okay.
Yeah.
It's a long time. I'll have enough time for questions even.
Do you have losses in the microwave as well?
Absolutely, we have loss in the microwave. We have hopes that the formulas that we introduce will have an exchange between the components in my system so much larger than the losses. Mm-hmm. And that's how we win over the losses. But absolutely, work with Magnon will introduce losses to your system. But that's why this is particularly useful using magnets, because the couplings are so strong that you can do things so much faster than any loss.
Yeah, okay.
Hopefully.
Great.
Well, as a proof concept and how nice coupling the microwave cavities to Magnons, we also worked with Professor Gregory Fuchs and Ezekiel Halperin. They will also give a talk here. See how lucky you are for next week if you'll be around. There are so many interesting talks on Tuesday and Wednesday. So Greg will probably, my guess is he will mention about this work where he took this organic insulating magnet. No? Hopefully. So he'll talk about this insulating organic magnet where you can actually deposit on anything, on any shape. So it's a thin film, it's a very long, and then we saw a very strong coupling that works in the strong coupling regime. So the coupling is like 9 megahertz and the losses are 30. So we overcome the losses here. But this has been shown many times over in the past. The reason this is interesting is twofold. One is the magnet is actually very, very tiny. So the magnet is like 300 nanometer against 6 microns against 600 microns. 600 is this long. And not only, it was interesting because of the strong coupling, we could see quantized magnetic excitation along the thickness. So this 300 nanometer, you can see the spin waves quantized along the thickness. Those are the signatures you see here. I know it could have a lot of explanation for those, but turns out that we tried many different approaches, and the most suitable theory to describe this was spin waves to those lines that you see here.
When you say that it's strong coupling, are you comparing G with the relaxation rate?
Correct. It's calculated as G squared. Oh, it's over there. So 4G squared over the two kappas, the two systems.
Okay.
Yeah.
Mm-hmm.
Coming back to my transducer. So after having a pause there. So how can the Magnon help? So the Magnon help by being near the microwave cavity. So what happens is, first, you have now a magnet coupled to your microwave photon, right? and the quantization here and here and here, well, I'll describe in the previous talk. And we hope that this coupling will be a lot larger than that coupling. This is a single ion. You can work on an ensemble, but the ensemble does not work coherently between the ions. But the Magnon does. At least on the uniform mode, everything is uniform. And if you excite Kittel modes, then you have a coherent behavior of those spins coupled to the microwave cavity. And the density of spins here is much larger than any spin ensemble. But it also comes with a coupling between the magnons and the ions. So I'm supposing here that you take your erbium and deposit inside the magnet. Well, this is the catch. So the catch is, in order for this to work for us, we need to have some sort of anisotropy in this exchange coupling. There's an anisotropy. It's very difficult to measure, produce, and effectively see, but suppose, theoretically we can do that you have some anisotropy in the interaction. So anything that causes a spin flip has a coefficient, and anything that has to do with the z direction has a different coefficient. We hope that this can happen naturally on a crystal, because we know crystals are very strongly anisotropic G tensors. So we hope that things connect, and then not the only hope. We have different pathways to overcome this, but in this simpler model, this is what we think. So why we separate the two couplings? We separate the two couplings because this coupling causes a shift in the spin transition. So you have a spin flip up and down, but this coupling shifts this transition a lot further as long as if it's too strong. So this is the Zeeman term, and this is an extra term caused by this exchange interaction between the ion, erbium, and your magnet. They have exchange interaction and cause spin flip. But it also causes spin flip, and the spin flip is a term like this. So we want this to be strong, because then the coupling is stronger. But we also have a downside, which is it goes with the volume, or square root of the volume. So we don't want this magnet to be too large. So ideally, we have some reasonable value for this magnet size. Well, it turns out that some people already measured in different ways the erbium-iron coupling. So the iron comes from the magnet, the erbium is my spin, and this coupling is super strong. There is no evidence of anisotropy in the system, but we know that the coupling can be terahertz. And that's bad for business, because terahertz will move this microwave to terahertz. So we lost our microwave tuning. So let's think on possibilities where we don't have such a strong coupling here, but we have strong coupling there. And let's see how this is possible. But before going to that, let me show why we should insist on having this system, or this setup. Well, we should insist because we calculated the transduction rate. What is the transduction rate? We have a cavity, so effectively you can describe, after the strong coupling regime, you can describe your system into cavity A, cavity B, something that goes here in between that converts the two population in the cavity. And then you have something going out of the cavity, something going out of this cavity, some going into this cavity. The transduction rate is what happens here in between, and kappa are the rates where the photons go into the cavity and out of the cavity. And for a perfect transduction rate, you want that everything that goes in goes out that way. And for that, you need something called impedance match condition, which is all those rates, they should match each other somehow. You don't want something too much faster in one side and too slow in the other side. You want them to match. So there's something called impedance match condition. And we calculated this for the system with a magnet. This is how it looks like. Don't go over each element in there. Let's look at some plots. And what you see is, because now we have a magnet, it's useful for us to tune the magnetic field. When you tune the magnetic field, Zeeman splitting, it split the spin up and spin down in a linear fashion. That's what you see here. And because now we have a magnet, you also see the signal from the magnet. It's this curve here that follows the Kittel curve. And we notice that it's especially strong, this transduction rate is especially strong near the crossing. You see this red region? So we want to operate our transducer near the crossing between the magnet and the spin transition. If you go further and now you plot the detuning, you notice something else. You notice that the transduction rate with the vertical axis here, it gets a lot larger as it goes close to a forbidden region, which breaks the diabatic elimination. So you don't want to work at resonance, you want to work off resonance, so you have a strong, you work on this adiabatic regime. And that's exactly where the transduction, but if you look at the numbers, you see that here the transduction rate is approximate omega, which has to do with my pump strength. And then, so I'm not winning by too much my pump. They are bothly working together. But now, if you have the magnet, we notice that you can increase this ratio by a lot. So you can work on a very strong regime very fast regime for the transducer and leave the pump behind in low level. This can be particularly useful. But not only, we notice that this keeps strong because we had the anti-crossing regime. This keeps it strong in between the two transitions. So we can work at a very large, much more broader range of parameter in this model. So that's why we should care. And then while plugging some facts here, some numbers, this is what I spoke. I should have presented this before. But the transduction rate goes like 10 megahertz approximately for this no magnet system. The coupling is about 100 megahertz. But as I said, J perpendicular should be less than terahertz, so you don't want to lose your spin. You want to have this anti-crossing, and then the transduction rate is faster, and you allow more detuning. But something that I should emphasize is that now you don't require this mode volume matching. What is this? So before, without the magnet, microwave and optical cavity, they should act on the same erbium spin. They both should act that. And you maximize this action by having both cavities at the same volume. But microwave and optical, they have very different wavelengths. You don't want them to have the same volume. So this also allows you to have this flexibility of not having cavities at the same volume, because your microwave will be coupled to magnet, and your optical will be coupled to spin, and the coupling between the spin and magnet is exchange. Then finally, you can plot the efficiency, how efficient this is, and you see, by looking at these two plots and comparing, you see that we can work, again, at much higher rate of coupling of photons going into the cavity and much lower pump, so we don't have those losses or those additional heatings to the system. So this red region is where the efficiency is the highest. So in this scheme, we can work at much higher couplings than without a magnet, where the efficiency is very high for very high omega. This is the conclusion. So this is basically a linear. This is this line in the very center of the red. It's this one, and in the very center of that region is basically this line. And then we see how the couplings should behave and how they compare, and what we can actually have an intuition of what's going on. So just plugging some values for people to look at. In my ideal system, what will happen? So let's plug some number that I idealized so you can see what happens. So first, as I said, we have 3 orders of magnitude here of difference between coupling. That's unrealistic, but that's based on the fact that we know that the coupling exchange can be terahertz, and we want to bring it down to gigahertz in the perpendicular direction. But if everything works out as planned, reasonable number for the decay rates, we are in the strong regime by many orders of magnitude. So even if the different couplings are not that anisotropic, we still have many orders of magnitude we can work with. We can relax a few things here and there in the theory, and we're still winning. So finally, let me just raise some ideas on how this exchange coupling can be engineered in different ways. So we have anisotropy not only relied on, we don't need to rely on the exchange coupling by having erbium inside the magnet. If we have, that's fine, but we need to find magnets where the exchange is not so strong, it's not terahertz. We need to find magnet with lower strength. Second is we can actually position the spins outside the magnet. If you position outside the magnet, like this, but very close, like 10 nanometer, in this case, the dipole coupling will be strong enough to raise two things. One, different couplings between parallel perpendicular. The difference is not so big. I did some estimations, but still you can have a factor of 2 or 3 different on the two couplings. But second, this is strong enough to be in gigahertz. So you have the coupling that you expect. And then you position your spin ensemble actually outside the magnet. This can be particularly useful because you can have this inside an optical cavity, and the optical cavity doesn't have the magnet in it, which causes additional absorption and decays. So having the magnet outside the optical cavity is actually good. Well, you can come with the fancier ideas that I don't have the correct implementation yet in mind, but we know the DMI actually is very anisotropic, and we have some, not for erbium, but for neodymium, you can see some DMI of half of gigahertz. So it can be very strong, and it's the anti-symmetry in the DMI that actually gives you this anisotropy in the two couplings. So it's natural in DMI theory that you have this anisotropy, and if you align, you need to align the magnetic field magnetization and along the DMI direction. But if you do that, you end up only with terms like this. Another strategy is to do not use microwave qubits or cavity, but to use this millimeter wave qubits and cavities, which is about 100 gigahertz. So as long as we have crossing between the magnet and the spins at 100 gigahertz, everything works out. So we only need to have an anti-crossing. And then everything naturally inherit from the previous calculation to this one at 100 gigahertz. And I want just to raise the idea, we have no clue if it works, but people have demonstrated, especially the Looking group in Harvard, they have demonstrated that they can engineer coupling at different strengths. They actually can suppress some couplings. They did it in the optical, in a very different setup, not solid state system, but imagine that you can do such a thing by having pulses. So they just have a sequence of pulses, smart way, and they can engineer some different interactions. So imagine that this is also possible in solid state. I don't know, but it's a possibility that we raise. So this is why this work is nice, because it actually opens a path and gives you new ideas. Crazy, but new ideas. So in summary, why should we use the quantum transducer is to disregard this mode volume compatibility. This will be very, very useful to engineer different types of transducers. We have a strong coupling. If you work in the strong coupling, you have those high transduction rates, and you also work in a larger parameter space by having larger detunings where you can work with. So the bandwidth is large. What is the cons? The cons will be highly anisotropic exchange is hard, and the optical absorption and the magnet decay also raises problem. Technological implementation might be difficult, but that's why it would be particularly useful. And with that, I want to thank once again the funds and people that collaborate with me. And I'm open for questions.
So, any question?
It's okay if not. We can talk later.
I'm a little worried that I'm going to embarrass myself, but I tried to follow, but I didn't quite understand why it's so necessary to get this anisotropy. Can you please re-explain that?
Yes,
Just to make it
absolutely.
really clear.
So the reason we need the anisotropy is we know that if you implant erbium in a magnet, this insulating magnet, the exchange coupling is in the order of terahertz. So that's what some experiment has demonstrated. And because it's terahertz, it will just take your spin resonance up and down far from microwave. So it basically splits this a lot further. So these two levels are not here anymore. This level goes up here.
Yeah.
And then now you are off resonance of your magnet. You don't have the anti-crossing happening, and it doesn't work.
Oh, okay, I think I understood that. So it's not that it's bad to have an isotropic exchange. You could have an isotropic exchange. It's that
Correct.
The isotropic component due to the erbium doping sort of drives you off resonance. That's the problem.
Correct.
Okay, thank you.
And the anisotropy is particularly useful if you have, because then you can keep this in gigahertz and that one in 100 gigahertz,
I see.
for example.
Okay, thank you.
That's just to tell you what
I
it
see.
can do potentially.
I
But
see.
it does work at some isotropic coupling too.
Okay,
Yes.
thank you. Thank you.
Thanks for the question, you see.
That's good.
So at some point, since we're now in this slide, you have a G factor there. At some point, they had a G factor tensor somewhere, maybe? My question is, you're in a solid. Is there a G tensor here that has non-zero matrix elements everywhere? Can I play with that since I'm in a solid?
Great question. It does have a G tensor, not in those slides. All of those G's, they're just scalars, and they go with the square root of number of spins that I have. The magnet is the number of spins in the magnet. With the ensemble, there is a square root of number of spins of the ensemble. But there is a G tensor. G tensor is not required to be anisotropic as the question, but the G tensor will relate the exchange coupling. So the exchange coupling happens in the spin, but because we have a spin orbit, the G tensor will, if you have an isotropic G tensor, we expect this to be reflected in the spin-spin coupling, which is not demonstrated here. I'm just being qualitative here, saying how the things are connected. But those G's are just scalars. I spoke about G tensor first for the question, and the second because I said that from the calculations of erbium ions in the same empirical model, we can calculate G tensor out of the wave functions that we have there.
Time for one more question. If no question, let's thank the speaker again.
Thank you.